Propeller slipstream and drag. It is very good not to have to compensate for the slipstream of the propeller, but nothing is for free. If you remember that the lift on a propeller aircraft is greatly influenced by the lift generated by the propeller slipstream on the wing area, you will realize that it is possible to vary lift rapidly by simply reducing or adding power. A typical approach power-off stall speed can be reduced by 10% at full power, a feature that can be smartly used to overcome many last-minute mistakes. And you can't profit from this spectacular effect on the turbofan aircraft. No lift bonus is available because the jet efflux is discharged clear aft and does not pass over the wings. Moreover, just as the propeller produces lift, accelerating rapidly under some flight conditions, it can be used to produce drag. When throttles are set to idle, the propeller produces drag, that is, negative thrust. The higher the RPM, the higher the drag. On the turbofan aircraft, however, the only practical means of producing drag appear with the provision of speed brakes, sometimes also lowering the landing gear. Imagine now a fast, clean aircraft facing the embarrassment of losing speed quickly when entering the terminal area or on the landing flare. We're not going to leave you in doubt. We will discuss the solutions later in this video. Poor acceleration times. In a turboprop installation, increasing power results in the required thrust being supplied quickly, something about 2 to 4 seconds to quantify what we say. Unfortunately, the turbofan engine is not that fast in respect to acceleration times. Thrust demands departing from a normal approach thrust to full thrust can be achieved rapidly, but from idle thrust to full thrust, things are quite different and can take about 6 to 8 seconds. This value can differ from engine to engine, so the full 8 seconds is a reasonable value to keep in mind. This acceleration delay can be of intense importance, especially during approach and landing. If flight idle is selected following a high and fast excursion above the glide slope at the lower end, the delay in getting enough thrust to recover the aircraft from the dive can cause difficulties for the crew. The engine should be reduced to idle only when the need for an increase of thrust has been removed. So add the poor acceleration response of the turbofan to the lack of possibility of increasing lift rapidly and the potential danger of the power-off operation, and you have reached 3 ways in which pilots of turbofan aircraft are not as lucky as the friend with the turboprop. Together, these facts are far more than enough to distinguish and emphatically mark the difference in one of the most significant aspects of operation of our 2 good aircraft power plant installations, the approach qualities. Engine operational recommendations. Because of the reservability of producing lift rapidly only by accelerating the airflow over the wings, speed is not that critical in recovering from a high rate of descent in the turboprop aircraft. We can say there is some room for error because you can still correct the mistake if you notice it before the flare. In the turbofan, however, there is little room for error because increased lift can be gained only through increase of airspeed of the whole airframe, which cannot be ascertained, or increase of the angle of attack, as we will discuss later on. The recommendations to cope with the delay in acceleration are very important. With a little bit of anticipation, it is quite possible to maintain the aircraft stabilized on the approach so that neither a drastic increase nor a dramatic power reduction is necessary. During approach, thrust levers should stay conveniently advanced to allow engine acceleration in case it is necessary to gain airspeed. Similarly, if an excursion to high thrust has been necessary to cope with a high loss of speed, don't leave thrust up for too long, or the airplane will go too fast again. Reduce thrust fairly soon, and you will fly on the target stabilized speed again conveniently. More will be said later when we discuss the aerodynamic matter involving turboprop and turbofans. We have discussed the modern transport needs for flying faster. There is no doubt that this is the trend of the aircraft industry. Flying faster determines some important aerodynamic characteristics of the jet aircraft, which we are starting to discuss right now. Aerodynamics. The key word to the top-level high speed is drag. Speed can be increased by reducing drag. Let's get into the theory of the airfoil to see how it works, diving into the aerodynamic aspects of the jets. To produce lift, the wing must pass through the air in such a way as to accelerate the air on the top of the wing to a speed higher than the air passing under the lower wing surface. The difference in relative pressure will result in an upward suction, the lift vector. The greater the difference in the lower and upper surface airspeed, the higher the difference in pressure. Hence, the larger the lift vector. But watch what happens when we accelerate the airfoil to speeds near the speed of sound. The local speed on the upper surface is higher than the free airspeed, and it is quite clear that airspeed over the wing can exceed or be very close to the speed of sound, although the airplane is still flying at subsonic speed. At a certain speed, shock waves start to form on the wing, and the compressibility effects become apparent. The speed at which the shock waves first appear is the critical Mach number. If speed is further increased above the critical Mach number, drag increases drastically. Buffeting is felt. Then the aircraft may suffer from certain stability and control deficiencies. The common sense signals that the jet should fly at the highest subsonic speed before compressibility effects, the shock wave we have mentioned, appear or become excessive. The exponential increase in drag must be solved with aerodynamic resources and design measures if we want to fly fast. Observe the conventional airfoil, normally used on turboprop aircraft, and then watch the supercritical airfoil, normally used in high-speed applications. The latter is characterized by very little camber in the forward portion. On the other hand, the rear portion is severely cambered. See what happens when forward speed increases. Both airfoils flying at the same speed. The shock wave appears first at the conventional airfoil and is delayed weaker in the supercritical airfoil. Hence, compressibility drag is delayed and weaker for the same speed. To reduce additional drag, jets have swept-back wings. All is done to make the wing believe it is flying slower than it really is. Let's remember how, in a straight wing, airflow through the wing is really perpendicular to the leading edge. By sweeping a wing instead, the velocity vector has two components, one perpendicular to the leading edge and the other parallel to the leading edge. This latter component can be seen to have no effect on lift or drag, since the air flows along lines of constant elevation. The pressure distribution is affected only by the flow perpendicular to the leading edge, and it results in a component less than the chordwise vector. It is apparent that the free stream velocity can be increased over one wing without sweep. That is, the critical Mach number of a wing with sweep is increased over one without sweep. This is why a high-speed aircraft has swept wings. The consequences of having a low-drag, high-speed aircraft can be discussed now. Like everything else, when you take advantage of something, you've got to absorb the resulting disadvantages. No pain, you can handle it. The first consequences of a high-speed wing is that it has poor lift at low speed. Poor lift at low speeds